We are solving problem 2 from exam 2 from spring 2018. This problem is about a heat exchanger. There's a heat exchanger. It's heating liquid benzene from 20 to 60 degrees isobarically. The surrounding temperature is 65 degrees C. The boiling point of benzene is 80 degrees C, so there's no vaporization effect, and we're given the heat capacity. So I'm going to call this CP. I'm going to just draw a surrounding. I guess the stream may not be part of the surrounding, but this is 65 degrees C. We have a P1 and T1, which is 20 degrees C, and P2 equals P1, and T2 equals 60 degrees C. Anything else? I think that's it. Part A says, using the input and output conditions, calculate the changes in specific enthalpy and entropy for benzene across this process. So students who took this exam would have had an equation sheet, and on this equation sheet would be formulas for how to change enthalpy and entropy for a condensed phase. I'll show you the formula here. Delta H would equal integral from T1 to T2 Cp dt, and delta S would equal integral from T1 to T2 of Cp over T dt. These expressions would also have terms that depend on pressure, but remember, pressure is not changing in this process. I might, if I were taking this exam, I would write these equations and come back later. It may also be worth putting in the numbers, but I'll come back to this. In part B, we're asked, assuming the heat exchanger could perform both heat and work, I don't know how it would do that, but let's assume it could, perform an energy balance on the process. What does the first law tell you about the relationship between delta H, Q, and W? So I would look at the energy balance equation. Again, in the equation sheet, it would look like this: dm U across the control volume, which is the unit, dt, is equal to minus delta H plus 1/2 U, lowercase u is the velocity squared, plus Zg m dot, mass flow rate. This is across the flow system, or it's actually pretty much the same as across the control volume. And then we have heat input, and we have the shaft work. Well, we are assuming steady state. Does it actually say that? No, but there's also no indication of a time dependence. So I think steady state is a safe assumption. And otherwise, the relationship would change with time. Usually we neglect these terms, unless you have a good reason not to. That's the typical thing to do. And that leaves us with delta H equals Q plus W. It didn't ask us to calculate anything, so we're done with that part. What is the maximum amount of heat exchange between the heat exchanger and the surroundings according to the second law? This seems like an entropy balance problem, so let's look at the entropy balance. ds total dt, again, we're going to assume it's 0 at steady state, is going to be the sum of the input stream entropies minus the output stream entropies minus Q dot over T plus S total generated. And the second law tells us that the entropy generation is greater than or equal to 0. I'm going to simplify this by just calling it m dot delta S. And this translates to m dot delta S is greater than or equal to Q over T, right? Because if the entropy generation is greater than or equal to, and this is moved to the other side, then m dot delta S is going to be equal to Q over T plus S total generated, which is greater than or equal to 0, so we can say this relationship is true. That also tells us, if we want to be more explicit, we can make sure that this is specified as the surrounding temperature. So what this tells us is that Q is less than or equal to T surroundings delta S. And so Q max, the largest possible value of Q, which is what the question asks us for, is going to be T surroundings times delta S. And delta S would have been calculated in this problem. So we will come back to that. And T surroundings was given, so we do know that number, 65 plus 273 Kelvin. Okay, next part. What is the ideal work done on the benzene system? Well, the ideal work would correspond to the reversible case. Remember, we have this delta H equals Q dot plus WS. This will tell us that WS min is going to equal delta H, which is known. We calculated it, or we didn't actually calculate it, but we would have calculated in an earlier part, minus Q max. And again, we'll come back to that. I do find it efficient to write out equations and show that you know what you're doing before spending time hammering out numbers. Okay, so the last part is what is the ideal, part E. Imagine the exchanger were part of a Carnot cycle where Q were calculated in part C being QH. And so what we call Q max is in fact QH, and TC is 15 degrees. What is the maximum work that can be extracted given those assumptions? Well, if we're talking about a Carnot cycle, I'd first look at the efficiency of the Carnot. So we're given the temperatures. This would be 1 minus 15 degrees over 65, which would be T hot. This actually comes out to 0.148, and this would be minus work output, I'm going to call it W net, divided by Q hot, which would be the required input. And Q hot would be the Q max. This would be this number. Okay, so if I were doing this exam, I might go to another problem rather than filling in numbers, but since we're making videos that are kind of contained to one problem at a time, I'm going to now crank out the numbers. Okay, so CP is given right here. So this is going to be, and it's constant. So the integral CP dt is just going to be CP times delta T. So it's 1.74 kilojoules per kilogram Kelvin times the delta T, which is 60 minus 20. I don't have to convert it to Kelvin because it's a delta. And this comes out to 69.6 kilojoules per kilogram. That's delta H. And delta S is going to be the integral of Cp over T. Again, Cp is constant, so it's going to be Cp ln of T2 over T1, which is going to be 1.74 kilojoules per kilogram Kelvin times the ln of 60 over 20 degrees C converted to Kelvin. And this answer comes to 0.223 kilojoules per kilogram Kelvin. Okay, remember that there are some dependencies. So later problems, okay, part B did not ask us to calculate anything. And let's see, okay, part C, we needed the delta S, which we just calculated. So that's going to be 0.223 kilojoules per kilogram Kelvin. And this brings the Q max to 75.3 kilojoules per Kelvin. So that is the answer for part C. And then part D, we needed the delta H from part C, which is 69.6 kilojoules per kilogram. And then I need to subtract Q max, which is 75.3 kilojoules per kilogram. Sorry, this was per kilogram. And the answer is minus 5.66 kilojoules per kilogram. And this means that ideally, work would be done, or it would be done on the surroundings, or we can say extracted. Right, so this heat exchanger is generating entropy, right, by heating from 20 to 60 at constant pressure, and also having a temperature of 65, which is not varying continuously from 20 to 60, there's an entropy generation. And in principle, if there were no entropy generation, if this process were done with a Carnot process, we could get the same temperature change, but also extract some of that energy as work. Okay, now, so they're asking us to use the Carnot formulas, but of course you are using different TC and TH. So I don't think it'll give you the exact same answer. But if we, let's see, okay, so that's QH, Q max is QH. So really the W net, and I'm going to put an absolute value, it's actually output work. and that's going to equal 0.148, which is the efficiency, times the Q max. So if you produced work just from a Carnot process that worked between the 65 degrees and 15 degrees, this is how much work you could get out of it, which is actually higher than part D. I think we're done.